Hello, everyone. Welcome to our today's colloquium. First of all, it's a great pleasure to have Mohammad Farazmand. He's a very good friend and collaborator. We have known each other, I think, for, I don't know, since 2016, maybe, after that time.
Probably, yeah.
Probably, yeah. A little bit about Mohammed's background. He studied mechanical engineering at Saudi University of Technology. He got his bachelor's in 2007. Then he did his master's in computational engineering and science at McMaster University under the mentorship of Nicholas Galerkin and Bartosz Protas. Then he did his PhD at PDEs under the guidance of George Haller. And then he moved to the States in 2014 for 2 subsequent postdocs. One at Georgia Institute of Technology, and then at MIT, where he worked with Temisapsis. And since 2019, he has been a faculty member at North Carolina State University. He's an expert in dynamical systems, turbulence models, including Navier-Stokes, and also data-driven methods. And today he's going to talk about Shape-Morphing Solutions for PDEs with Conserved Quantities.
All right, thank you very much, Status, and thank you everybody for coming on Friday, pretty late on Friday. I appreciate that. So, as was mentioned, I'll talk about this method we've developed that I call Shape-Morphing Solutions for PDEs. This is a numerical method for approximating solutions of PDEs. This is joint work mostly with my former PhD students, William Anderson and Zach Hilliard. So here's the outline. Oh, this went too fast. There we go. This is the outline of the talk. First, I'm going to motivate the talk and explain a little bit. I feel like I'm obliged to explain, given that there are so many methods for solving PDEs, why yet another method is required. So I'll motivate this at the beginning a little bit, then introduce you to the idea of shape-morphing solutions in that context, and the equations that govern the revolutions, and then some computational aspects of these kinds of solutions. And if there's time left, I'll give you some results related to data simulation with these shape-morphing solutions, or SMS, as I will refer to them for short. And throughout the talk, I'll give you numerical results regarding SMS. All right, so here's the general setup of the problem. I have a very general form PDE. It's time dependent, so that the solution U depends on time and space, and its rate of change is given by some differential operator. It can be nonlinear. It also can be linear, but most of the examples I'll show you are nonlinear PDEs. My spatial domain is d-dimensional. Usually in the examples I'll show you, it's either 1, 2. There is one example that is 8-dimensional, this space. And there we really, I hope that you will really appreciate the value of this framework for solving PDEs in very high spatial dimensions. It depends on time, and the solution space, the values of U are scalar valued in R. For simplicity, but it's easy actually to generalize it to to vector valued, in fact, solutions, and even complex valued PDEs. I'll give you examples of actually each of those. So the true solution of the PDE, I'm going to denote by U. At any time t, I'm going to assume it belongs to some Hilbert space. For simplicity, just think of H as L2 usually, but it could be Sobolev spaces as well. I'll mention that all I will talk about today is about strong solutions of the PDE. So I will not discuss weak solutions. Therefore, I'm assuming that the solution has enough regularity. The approximate solutions of the PDE, numerical solutions, I'm going to denote by U hat to distinguish it from the true solution. And it's going to belong to some subset of this function space H. We'll see in the case of shape-morphing solutions that this turns out to be a manifold, this space M. Now, a lot of PDEs that at least I encounter come from physical models, and they conserve certain quantities. For instance, mass conservation, energy conservations are built into these PDEs. Now, when you discretize a PDE to numerically solve it, oftentimes the discretization, if you're not careful enough or don't work hard to design the discretization in a special way, they may not necessarily also conserve these physical quantities. What I will discuss as part of this talk is that in the framework of shape-morphing solutions, we can easily actually make sure that the discretization or the approximate solution conserve whatever physical quantity the true PDE conserve. Whatever these quantities are, I'm going to denote them with IK, I for invariant. These are maps from function space to the real line. And the invariance of these quantities or conservation of them implies that they don't change over time. The number of conserved quantity for the PDE in general is M. So that's the general setup for our problem. Now, this is a little eager to get to the end of the talk. All right, I think here is where I want it to be. All right. Now, once you're given a PDE like this, if you look at the Galerkin type methods for solving a PDE numerically, what you typically do, you approximate or express the approximate solution in terms of a linear combination of certain modes or basis functions, trial functions, right? Depending on the type of PDE and the boundary conditions you have, these functions of space can be Fourier modes, finite elements, could be data-driven discovered modes like proper orthogonal decomposition modes, or dynamic mode decomposition could be used to find an appropriate basis. But when you decide on some basis, but eventually in Galerkin approximation, at least you write the approximate solution in this form where you're kind of implying a separation of variables. You have time-dependent amplitude and space-dependent basis functions. And the question is, how should these amplitudes evolve so that this is really an approximate solution of the PDE? And the usual way you go about it is that you realize that this lives on a finite dimensional subspace of your function space H. This is a span of UIs. And the right-hand side of the PDE at any point of this form may not really live in this subspace necessarily. So what you do is that you take that right-hand side and you project it in some suitable manner onto this subspace, and that tells you what should be the rate of change of this U hats. That's U hat sub t. That's the projection of the right-hand side of the PDE, and you get a set of ODEs for evolution of the amplitudes once you do that. And you solve the ODEs numerically, and you plug it back into this expression, and you have your approximate solution. Now, note that before we go any further, this Galerkin projections or Galerkin type methods, it's well known that it's not guaranteed that if you have conserved quantities in your original PDE, this approximate solution will also conserve those invariant quantities. That's one of the drawbacks of Galerkin methods. But more importantly, what is a feature of them that I don't like a lot is that these modes, once you decided on what they should look like, Fourier, finite element, or otherwise, they're static in time. They don't change. They're fixed. They only depend on space. However, in a lot of PDEs, that's not desirable. The reason is that if you're looking at fluid flow past the cylinder or atmospheric flow on the globe, there are a lot of localized structures that get advected over time. They move around, they change the shape, their length scales change at the same time. It's not very efficient, therefore, to have basis functions that are globally defined and they do not adapt to these localized features of the solution, whether they are jets or vortices. Same problem appears in waves, where you have usually wave packets where a lot of action is happening in a part of your subdomain, but not everywhere. So you want your basis not to be globally defined, but somehow be tethered to these features that are moving around and changing shape over time. The main idea of shape-morphing modes is basically this, to allow these basis functions, UIs, to change in time. And the way I encode that time dependence in the basis is through a set of parameters beta I that I'll call them shape parameters, so that as time evolves, these shape parameters change. As a result of that, the basis also evolves. And if I choose my shape parameters and their evolutions cleverly enough, the hope is that this basis function adapts to the actual solution of the PDE and will be more adept at capturing those localized structures as they evolve over time in the spatial domain. So that's really the main idea. I'll elaborate a little bit on that.
So you always
yes.
start with assuming that the solution is a sum of some basis.
I do, yeah. There is generalization of this that already has been done to more general forms that are compositions of functions as well, like a deep neural net. I'll mention this in a second as well. But for most of this talk, I'm going to assume that they're linear combinations. Yes. All right, so shape-morphing solutions, as I said, have this general form, time-dependent amplitude, like Galerkin type solutions, but also they depend on these shape parameters, beta I, each of them. The phi, which is the basis function, I'm going to call it the shape-morphing mode or shape-morphing basis. Note that on the previous slide, each of these modes were different, and in general, I can make them to be a different function. One could be a Fourier, one could be a Gaussian, the other one could be a finite element. But for simplicity, from now on, I'm going to assume that they are all of the same type. If I pick Fourier modes, they're all going to be Fourier modes. But then the difference, what makes them different in different terms is the way they depend on the shape parameters. All of these parameters together, I'm going to call theta, including the amplitudes and the shape parameters. Both depend on time. Oops, I realize there's a typo here. This should be theta, not q. Let me give you a couple of examples that are actually pretty tangible, and people have used them in various contexts before. Like Gaussian mixture models are an example of these, where phi is a Gaussian, and the shape parameters are the mean and covariance of the Gaussian. Now, in Gaussian mixture models, you usually train your model and you fix the mean and the covariance, and they never change in time. What is different here with shape-morphing modes is that we allow the mean and the covariance to evolve over time as well. I'll tell you a little bit later how I evolve them, but for now, I accept from me that they are time-dependent parameters. Another example of this is shallow neural networks, and as I just mentioned, deep neural networks also the same. Here, phi in this context would be, if you're familiar with neural networks, would be the activation function of each node, and the weights and biases of the neural network would be my shape parameters. Again, in neural networks, you train them, and then you find the optimal shape, the weights and biases, and you never change them with time. In this context of what I'm talking about, shape-morphing solutions, I'm going to allow them to change over time. Another example is wavelets, where the wavelet functions is my phi, and the parameters would be translations and dilations. I forgot to draw your attention to this formula. In the case of Gaussian mixture models, the exponential is my phi, the shape parameter is the mean and the variance, and the amplitudes are these alpha i's. So it's an explicit example here. Now, before I tell you anything about the evolution of these parameters, how they should evolve, let me give you two different interpretations of this shape-morphing solutions. One is geometric, one is in the context of neural networks. The next couple of slides are the essential parts of this stuff. The rest of it is like technical derivations and the things that you can go find in my papers and numerical examples. So really the take-home message in the next couple of slides. So the geometric interpretation of SMS is the following. As I mentioned earlier, the conventional Galerkin type methods, your solution evolves on a flat subspace of your function space. It's a finite dimensional subspace of your function space, in other words, where these UIs did not depend on time. But the right way in geometrically to think about shape-morphing solution is to think of them as a manifold immersed or embedded inside your function space instead of it being a flat subspace. And the reason that it's not flat anymore here is that the solution now depends non-linearly on some of these shape parameters. More precisely put, this solution space, this manifold, is actually a graph over the parameters of my solution. So for each theta that I pick, I get a point on this manifold. This manifold is finite dimensional because I have finite number of parameters. However, note that it's unusual in the sense that the manifold is inside an infinite dimensional function space, meaning that every point on this manifold is a function of x itself. But nonetheless, it's a finite dimensional submanifold of that infinite dimensional space. So that's the geometric interpretation of shape-morphing solutions. And again, I still haven't said anything about how to evolve the parameters. I come back to this and tell you how to write down equations for the evolution of these parameters. But once you have an evolution, that evolution corresponds to a curve in the parameter space, which under U hat maps to a curve on the manifold. And the rate of change of the approximate solution becomes the tangent curve onto the of this curve, which is bound to live in the tangent space of the manifold M itself. Keep that in mind, that's going to play an important role in a little bit. The second interpretation that I promised you is their interpretation as neural networks. It's not so much an interpretation, actually, than the neural networks that, as the way I will describe them, are a special case of shape-morphing solutions. In the following sense, in a neural net, in my context, the inputs are going to be the spatial variables, the coordinates of the spatial variable x1 to xd, and the output is going to be my approximate solution. Each node of the neural net, this is a shallow neural network because it has just one hidden layer, but you can generalize this to deep neural nets too. If you look inside each node, usually in neural nets, you multiply the input with a weight function, weight parameter, which is W, this is a matrix, and you add a bias bi here for node I, and then you apply an activation function phi, which could be a sigmoidal function or tangent hyperbolic, for instance. And the output will be this activation function applied to this expression, and then you add them up. This is the output of the ith node, but you add up the outputs of every node with an output weight alpha I. That's in the amplitudes in the shape parameter, in the shape-morphing solution. As I had alluded to before, the crucial difference here is that unlike conventional use of neural networks, now the weights and biases of my neural net depend on time. I have to prescribe how these things change over time. Yes?
I'm having a hard time conceptualizing how this is different from training.
As I will explain, there is no training needed in this. I can write down explicitly what are the differential equations that these parameters need to satisfy. I don't need any input into any data in the traditional sense of training, that I don't need input data and output data.
Okay,
In
but
that
you still have input data, which is driving the network, and you still have an output, and you're making some decision on how to change the weights and biases based on that.
Right.
So you could technically say you're training the network, right? Even though the algorithm might not be stochastic approximation or whatever.
The training is in the sense that if imagine you have a neural net which has one-dimensional input, one-dimensional output, right? Mm-hmm. Classically, when you train the neural net, you feed in a lot of those one-dimensional observations, the inputs, right? Mm-hmm. The more you feed in, theoretically, the better your neural net performs, right? Here, I have really no observations to feed into this. In other words, my x1 to xd are not really observational data that I'm, or measurement data or numerical simulation data that I'm feeding in. Hopefully, when I write down the equations of motion for the parameters, it will become more clear. Yes?
You're projecting the dynamics onto the manifold and by the parameters of the neural network. But one question would be, if you have so many parameters and the expressivity of the neural network is so large that basically the same dimension as it's very large dimension, and you're not recovering the intrinsic coordinates of the solution space, and there's no advantage of using this method. So how do you make sure you're approaching the true dimension of the solution space?
I think your question is related to the over-parametrization, right? You don't want to necessarily over-parameterize your network, and I sympathize with you that, yeah, you don't want to do that. The way we work for it, we don't have a criteria that stops you from over-parameterizing. We start with a pretty low-dimensional network and then increase it until we reach a good error tolerance that we're happy with.
So we're trying to get a point that when you increase the parameter, when you decrease the parameter, the solution get really bad.
Yeah.
That's the point.
Yeah. Mm-hmm. Was there another question, I guess? No. All right. As I said, this can be and has been actually expanded to deep neural networks. I want to give credit to Tamer Zaki's group who actually did this in the context of deep neural networks in this PRE paper. But as I said, turns out that these kinds of networks are a special case of shape-morphing solutions. So it's good to have that interpretation in mind as well. All right, so far, as I said, I hadn't told you anything about the evolution of these parameters. So let me say how we decide how the parameters of the network, or more generally, the shape-morphing solution would evolve. If I plug in my general form of the shape-morphing solution into the PDE, it will not satisfy the PDE. It's an approximate solution. So what I will do, I'm going to look at the residual, which is the discrepancy between the left and right-hand side of the PDE. This depends on X because the approximate solution does depend on X, but also depends on theta, and also theta dot. And the theta dot part comes from the fact that the time derivative of the approximate solution, if you apply chain rule, will depend on the rate of change of the parameters. Now, a geometric picture of it is through the manifold interpretation that I said. You have your solution at a particular time over here corresponding to certain parameters theta time t. And like Galerkin approximation, the right-hand side of the PDE is not bound to live in the tangent space of this manifold. The procedure that I will explain, what it does is that it projects the right-hand side onto the tangent space of the manifold. Now, what is different with Galerkin projections is that in the conventional case, the projection does not change over time because your subspace is flat. But here, your solution is evolving on this manifold, and therefore the tangent space is changing. So when you're projecting, you're updating the projection as you evolve along this manifold. In order to minimize this residual, the discrepancy between the left and right-hand side of the PD, I look at its norm in my function space square, and then I minimize it in an instantaneous fashion in the sense that I say for any particular time t, change theta dot in such a fashion that in that particular time, the residual is minimized. And I have an additional set of constraints in case my PDE has conserved quantities that I care about, and I want to make sure that my approximate solution also respects those conserved quantities. So this is an instantaneous constraint optimization problem that forces my solution U hat to respect the conserved quantities of the PDE. Now, one side note here is that when we were developing this, I told my student William, who was working on this, that it's probably better to look at not this instantaneous optimization, but look at the finite time error, which means that you also integrate this over some time interval 0 to t, and then write down the Euler-Lagrange equation to find the minimizer. Unfortunately, it turns out that at least on some simple cases that we worked it out, this leads to unstable equations for theta. I won't go into details of this, but if you're interested in the appendix of this paper, we split out that how things can go wrong with the finite time optimization. We stick with this finite or instantaneous, type constraint optimization. Now, in order for this optimization problem to be well behaved, I need some assumptions. I'm going to make the following set of assumptions, but let me first make formal the definition of this manifold that I've been talking about. This is all functions in my function space for which there is a parameter theta such that that point coincides with one of these shape-morphing solutions for some parameter theta. Now, I make the following assumptions that, first of all, this U hat function that I choose is once this differentiable is in parameters. It should be sufficiently differentiable in space, depending on the right-hand side of my PDE and what kind of operator I have there. And most crucially, I assume that this map U hat from the parameters to the function space is an immersion, which in straightforward words, it says that the partial derivatives of the solution with respect to parameters are linearly independent. And that ensures that the tangent space at every point on the manifold is actually full rank. So the projections I'm going to define or use are well defined. And the gradient of the conserved quantities of my PDE with respect to these gradients or respect to these parameters theta, I'm going to assume that those are my conserved quantities are such that those parameters are, those gradients, excuse me, are also linearly independent. These are finite dimensional vectors. And this assumption I have never seen being violated in practical applications where these conserved quantities are like mass, momentum, and things like that. Okay, so with that, those assumptions, let me introduce a little bit more notation on this slide for me to be able to state the main result. Is the following. I introduced the metric tensor, which is the inner product of the partial derivatives of my approximate solution with respect to parameters. You can see by inspection that it's a symmetric matrix, and in fact, it's positive definite under the assumption, three assumptions that I had on the previous page. And the right-hand side vector field that I'll use on the next slide is defined as the inner product of the right-hand side of my PD evaluated at the shape-morphing solution, inner product with the partial derivatives of SMS with respect to its parameters. And then for the constraint part of the equation, I defined a constraint matrix, which has this form, the gradients of the constraints inverse of this metric tensor. And then there is a vector B whose entries are given by this expression, where F is this vector field that I defined over here. Under the assumptions that I specified, it's easy to see, as I mentioned, that M is symmetric, positive, definite, and so is C. Both of these matrices are invertible. One perhaps note that is worth pointing out is that this M is n by n, the number of parameters in my solutions, but this constraint matrix is usually small because it has the number of conserved quantities of my PDEs. If my PDEs have a handful of conserved quantities, usually this is a small matrix. But this could be a pretty large matrix depending on how many parameters you have depends on. And so think of a very deep neural network or very wide, shallow neural network. So this n in those cases can be quite large. Now, here's the theorem that tells you that the optimization problem is well behaved, basically, and tells you what the solution is. Under the specified assumption, this constrained optimization problem, if it has a solution, its solution would have to satisfy this equation, where M is the metric tensor, F is the right-hand side vector field I defined last time. This is the rate of change of the parameters. And this expression is a linear combination of the gradients of the conserved quantity with some Lagrange multipliers that enforce these constraints, where the Lagrange multipliers satisfy this linear equation. And as I said, again, C is a small matrix typically, and so it's not too hard to solve this linear problem numerically, or linear equation numerically. Now note that I said in a second, maybe slyly, that if a solution to this problem exists, then it satisfies this equation. You may ask, could it not have a solution? And actually, it could be the case that this does not have a solution. And it would be, it happens that it may not have a solution if your problem is over-constrained. In other words, if your approximate solution depends on too few parameters, n is small, but you have a lot of conserved quantities, such that the intersection of the hypersurface or manifolds that each of these conserved quantities defines, this intersection can be even empty if you have too many of these conserved quantities. But you can get around with that by just looking at the richer model, which has more parameters in there, and rectify that problem. If your PDE doesn't have conserved quantities that you care about and you want to enforce, so that you don't have this constraint, this term goes out, you just end up with this equation. And then in that case, the unconstrained problem has always a solution, and the solution is unique. You can prove that. So that has these nice properties. Another nice thing about this method is that the Galerkin truncations for PDEs is a special case of this SMS. If your manifold happens to be flat, then the equations that I just described in theorem reduce to the usual equations that you're familiar with Galerkin truncation. All right, with that, let me give you a number of numerical examples and then switch to some computational considerations when we want to implement this methodology. The first example I'll show you is the so-called leapfrogging dynamics of vortices. The PDE in this case is the vorticity formulation of two-dimensional Navier-Stokes, where omega is vorticity, u is the velocity field of the fluid, and psi here is the stream function, which relates which gives you the velocity field. And in fact, there's a relationship between the stream function and also vorticity. In this example, we just decided to express our approximate solution in terms of the stream function, because if you know the stream function, then you know the velocity and you know the vorticity. So we started with the stream function, and our approximate solution has this form. It has time-dependent amplitudes, and each of the modes is an exponential, it's a Gaussian, with time-dependent centers and length scales. This just tells you how spread out the Gaussian is, this L, and xi tells you where your Gaussian is. The reason for it is that we're looking at vortex dynamics, and these vortices kind of look like Gaussians. So it made sense to use an expansion of the Gaussians. The conserved quantities that we enforce in this case are energy and entropy. Energy is just kinetic energy, u squared, integrated over the domain. Entropy is vorticity squared, integrated over your domain. It is now well known, this leapfrogging motion of vortices is that when you have four vortices like this, two of them are positive on the top, two of them are negative, so they're rotating in opposite directions. What happens is this funny motion where two which are behind, they speed up and go between the two in the front, and then they switch places, and they keep doing this oscillatory motion forever and ever. The video that I'm showing you is the solution with this approximate solution with just four terms, because we have four vortices, so it makes sense to just stop at four. And if you do a high resolution simulation through a different method, numerical method of these vorticity equations, you get evolution very similar to this. In fact, what we did is that we looked at point vortex methods for solving these equations. And here what you see is the comparison between the point vortex method and our method, and the circles are the SMS solution, and the solid line is the point vortex method, and they're in excellent agreement with each other. It's just a sanity check to make sure that the solutions are accurate. The next example is the one that Status is gonna like. It involves NLS. In another thrust of my research, I work on extreme events and particularly ocean rogue waves. And nonlinear Schrodinger equation is a pretty good model for that. Rogue waves are surface waves in the ocean that over time, they just grow to incredible amplitudes. And they're very dangerous to ship, and you can imagine aircraft carriers and stuff like that. So there's a lot of practical interest in understanding them. Nonlinear Schrodinger equation, admittedly, is a toy model describing those waves. It is different from the previous PDE that I showed you in several crucial ways, but especially that U here is complex valued. It's not real valued anymore. I here is your complex number. And I look at the cubic NLS, where you have this cubic nonlinearity in there. And the solutions, approximate solution shape-morphing solution that I will look at is of this form. It looks a little weird. It kind of looks like a Gaussian, but then it has this term which is complex, this term which involves the phase. V is called the velocity, which really is not the velocity in the normal sense that we understand. It really does not describe the velocity of the waves moving, but people call it the velocity anywhere. L is the length scale, which tells you how spread out your wave packets are, or how localized they are. This is not my invention. This has been used in optics for approximating solutions of NLS and linear version of it, which looks like the Schrodinger equation. So we took this from this paper. And the conserved quantities that we decided to enforce in our approximate solution was mass and energy, which have these forms. This is really the Hamiltonian for this PDE. It turns out to have a Hamiltonian structure. And there are two types of solutions that you usually encounter when you simulate these. There are some that, if you start with a very large amplitude compared to the length scales of the wave packet at the initial time, that wave packet over time decays in amplitude. That is this example. If you start with the right initial condition, in the sense that the amplitude and the width of the wave packets are just the right size, then they grow over time. And these are the ones that I'm more interested in because they mimic the rogue waves that grow over time. So the question is, can we write down the evolution equations using the methodology that I explained, and do they agree or at least approximate these solutions? The answer is yes, to a good degree, and more importantly, that it is much more accurate than other methods that people have used in the past. For instance, if I look at this decaying case where the amplitude decays over time, this is the time series of the amplitude, the maximum amplitude of the wave. In the decaying case, the black one is the really accurate direct numerical simulation. The blue is our method, which is SMS. It tracks pretty well. But if you use a POD, if you're familiar with proper orthogonal decomposition, it's a very popular reduced order modeling method. If you use POD modes with 4 modes to write down a reduced order equation, then you get this evolution in red, which has nothing to do with reality, really. Now, I use 4 modes because if I go back to the previous slide, you see that I have 4 parameters in my SMS. So it's 4 modes, 4 parameters. It's a fair comparison. Eventually, if you use POD modes, I think if you go to 12 modes, then you capture things very well. But to be a fair comparison, I only use 4 modes. Same thing for the case where you grow, the one that mimics rogue waves. The DNS is black. This time, the agreement is not as well. Our solution peaks slightly later in time and goes slightly over the true amplitude, but still not bad for one term approximation of this PDE solution. And again, look at what the POD approximation does. The POD approximation is, again, very off from reality. Okay, as I promised, I will talk about some computational aspects as well. I believe I have about 20 minutes, right, or so. Okay, all right, so now there are problems with computationally, some of which we have addressed with this method that I will describe now. One is that the SMS equations, the equations that tell you the evolution of the parameters of the model, can be very stiff. In this case, I've dropped the terms involving the Lagrange multipliers that enforce the conserved quantities. It's not the main focus here. Those are well-behaved and nice. But nonetheless, this term, the SMS equation, turns out that the metric tensor, this M, although it's symmetric, positive, definite, it's usually very ill-conditioned. And as a result, these ODs are very stiff to solve. Like if you use this explicit time integrator like Rangakuda, explicit Rangakuda, it forces you with adaptive time stepping. It forces you to take very small time steps to evolve the parameters in time. You could go around this by using an implicit integrator, like implicit Euler or something, and then you can take much larger time steps. But I like explicit methods because it has nicer features for me to use. So we wanted to do something about the stiffness of the problems, and the solution that we came up with, which I'll describe to you, is the so-called regularized SMS. The other problem is that evaluating the metric tensor and this right-hand side vector field can be computationally very expensive because it involves computing a lot of inner product over the function space H. If n is large, the number of parameters, then you have order n squared inner products to compute, and that can be expensive, right? And as you're evolving in time, you have to compute these over and over, right? So it just becomes computationally difficult. We have come up with 2 remedies for this. One is called symbolic SMS that I'll describe, and another one called collocation SMS. All right, let me start with the regularized SMS, which deals with the conditioning of the matrix M. The solution is pretty intuitive. Whenever you have least squares problem and you get matrices that are ill-conditioned, you regularize your least squares problem, right? Here is the same story. We regularize the underlying optimization problem that gives rise to the SMS equations by adding an Tikhonov regularization with regularization parameter alpha. Again, we can have constraints or no constraints, doesn't matter in this case. And the solutions get modified to this very similar looking equations, except that the M is added with a scalar multiple of the identity matrix. By the way, if you make this assumption, then your approximate solution you have does not even have to be an emergent. The equations and the optimization problem are well defined, even if that assumption is removed. And that has worked pretty well. I'm still not too happy about this, to be honest with you, because whenever you have regularization, then you have to ask the question, what regularization parameter do I pick? And some arbitrariness comes into play there. You could say, why did you do L2 regularization and not L1, right? Valid questions. The design choices come into play that I'm not a big fan of. But nonetheless, for practical computational purposes, it has worked pretty well. I'll show you some examples in a second. Now, in the second computational bottleneck, which was computing a lot of inner products, turns out that if you can use Mathematica or Maple or something to compute your inner products symbolically, get symbolic expressions for them, then you're in luck, because it turns out that this matrix and the right-hand side have a very special structure that if you compute a k by k block of them, where k is the number of shape parameters beta in each of these terms, usually these are a handful, like 4, 5, 6 of them. Once you compute this symbolically, then everything else you can populate without computing any additional symbolic computations. With direct substitution, you can compute all these other blocks in the matrix. And similarly for the right-hand side, if you compute the k-dimensional block of the right-hand side vector field, everything else can be populated. Now, this is very appealing because no matter how many terms you have in your system, the computational cost reduces to order k squared instead of n squared. N can be very large, but k is usually the number of shape parameters, usually very small. Again, usually handful of parameters. So this has sped up when we were able to symbolically compute these inner product. It has sped up tremendously, as I'll show on numerical examples, our computational capabilities. However, not always these inner products, when you put things in Mathematica, will give you useful symbolic expressions. Sometimes tells you I cannot simplify the integral. And it can happen sometimes, especially when you're dealing with shape-morphing neural networks, where the activation function can be like tangent hyperbolic. Turns out Mathematica doesn't know how to integrate this. So what would we do in those cases? Well, in that case, we have introduced collocation runs, and the idea behind that is that its starting point is similar. We define the residual in the same way, but instead of minimizing the norm, the functional norm of the residual, we minimize the sum of the residuals at certain collocation points that we decide where they should be. And the similar Tikhonov regularization, if needed, can be added, and the same machinery of conserved quantities as constraints. And it gives you a set of equations that look like this, where now this matrix has no inner products involved in it. It's just a partial derivative of your solution evaluated at the collocation point. It's not even necessarily a square matrix anymore. It depends on how many collocation points you have. And the right-hand side matrix, similarly, is your differential operator applied to the approximate solution, and then evaluate the result evaluated at the collocation points. So you do away with computing inner products altogether if you go with the collocation estimates. So let me show you some examples of this. This is a solution of the Fokker-Planck equation, where the underlying stochastic differential equation is the Dopping oscillator with some Brownian noise, Brownian motion added to the right-hand side. And what the Fokker-Planck equation describes is the evolution of the probability density of where the particles in the system would be. So P is a function of time, and x1 and x2, or x and y, which are the two coordinates in the Dopping oscillator. The conserved quantity in this case is conservation of probability. So if you integrate your probability densities, has to add up to 1. So we have this natural conserved quantity that we also enforce. In this case, again, Fokker-Planck lends itself, or it's very natural to try to approximate solutions as a sum of Gaussians. And Gaussians, doing symbolic computings with them is very straightforward. So what I'm doing here is symbolic SMS, where I'm computing all the inner products with symbolic computations. If you do that, then you can integrate this Fokker-Planck equation in 13 seconds to generate this movie. But if you do not and try to approximate the integrals with some Monte Carlo method, the integration takes 2.5 hours almost, right? So this symbolic SMS really speeds things up. And the key again is that you do not compute all entries of the metric tensor, only a small subblock of it. Now, we got a little bit very excited with this result and got a little bit ambitious. By the way, let me actually point out that the solution has 30 Gaussians in it, and initially it started with 15 Gaussians over here and 15 Gaussians over there. That's when you see at the very beginning 2 dots. And then Gaussians over time, according to the SMS equations, evolve to where they should evolve, and then give you this very nice PDF of the solution of the Fokker-Planck. So there are 30 Gaussians underlying these solutions, by the way. All right, so we got a little ambitious and we said, all right, we have the Fokker-Planck equations where the PDF is a function of 2 spatial variables. What if we have more spatial variables? And in Fokker-Planck's situation, it's very easy to actually come up with more variables. We looked at stochastic differential equations of this type, which basically describe the evolution of interacting particles, where we have 8 particles in this case. These 8 particles in the Fokker-Planck equation give rise to a density that depends on 8 spatial variables, right? Now, if you've tried to solve PDEs in 2 or 3 dimensions, you know that 3 is already pretty hard and time consuming. Now, imagine you want to solve a PDE which has 8 spatial variables. If you try to use finite elements or finite difference, discretize it in any way, it's just out of control. 8 spatial dimensions is too hard to do. So you really need to use a meshless method like the one we use, where we don't really discretize the space. The discretization is implicit into the Gaussians that expand the approximate solution. So in that sense, you can think of the method that I'm talking about as a mesh-free method. And it works really well for this problem. Now, in 8 dimensions, I don't know how to visualize 8 dimensions. So what I'm going to show you is not the solution itself, but the relative error of the mean of the solution of the Fokker-Planck and the covariance. And here is the errors that you expect if you do not enforce that the integral of the density should add up to 1. The errors are not bad, but they grow around to 1% or so over time. And same thing for covariance, even larger than 1. But if you enforce this conservation law into the solution of SMS, which as I explained, you can do easily in our framework, then the errors really stay quite small for long amounts of time. In terms of the computational time, it takes about an hour to do these computations, get these solutions. But again, remember that this is 8-dimensional PD. So an hour is pretty reasonable for that. The relative error is 10 to the minus 6, as you see, for the mean, and around 10 to the minus 4 for the covariance. If you try to do same solution of this through Monte Carlo methods to estimate the PDF through Monte Carlo methods with adaptive sampling and all that fancy stuff, the time integration, the solutions take more than a day to obtain, and the errors are also worse than what we can do with SMS. The next sample is another PDE we looked at, which maybe I should skip this one, and let me see, which one do maybe I'll skip the data simulation one. I just show you this last example for the Kuromoto-Sivashinsky equation. This is a PDE that involves 4th derivative in space, pi derivatives. And this is the first example where I'm going to use a shallow neural net to approximate the solution of the PDE. Where, remember, in that case, the right interpretation of the shape parameters are the following. The amplitudes are the output weights of the neural net. The shape parameters are the bias and the weights in the neural net. It's a 1-dimensional PDE, so my x is 1D, and therefore my weight matrix is really a scalar, time dependent. And the activation function I use is just a tangent hyperbolic. I'm going to use 10 nodes, which means I have 10 terms in here. And Here is the case where I use collocation SMS, because if I wanted to use symbolic computing, because of the tangent hyperbolic, I could not get any useful symbolic expressions for the inner products that I need. So I instead use the collocation method with 128 collocation points. And for comparison, I also use a Monte Carlo method for approximating the integrals with the same number of samples, just to see the accuracy and the computational time in them. Here is the DNS solution, the ground truth. Here is what you get from the Monte Carlo approximation of the inner products. Not bad, you know, gives you very similar solutions. And here is the SMS solution, which is very similar also to the Monte Carlo and DNS. But if you look at actually the absolute errors, or this is not even absolute error, it's the difference between the truth and these two numerical solutions, you see that the Monte Carlo, actually the errors start to grow about 20 time units. But for our method, the errors stay small for a longer amount of time. Now, in terms of computational time, the Monte Carlo method takes about more than 3 hours. For us, it takes about a minute and a half or so. And the errors are also smaller than using the Monte Carlo method. Let's see. Did I say that? No, I actually stated that. This is the time for the Monte Carlo method is about 3 hours, but for us it's in terms of seconds. In seconds we can do it with the collocation method. The error for Monte Carlo is over 100% eventually at the final time, but for us it stays small, about 3% or so. Okay, let's see. I probably have time for a couple of minutes. 3 minutes? Okay. Maybe I'll very quickly tell you a little bit about the data simulation. Now, in PDEs, we are happy when we have a good enough method. We are happy to just supply some initial condition to PDE and solve it. And that's fine. But for practical applications, where imagine you have a PDE that forecasts weather for tomorrow, right? You have to supply the initial condition that corresponds to today, right? You cannot just supply an arbitrary initial condition. And measuring the initial conditions for the PDEs is not an easy task. You have to run experiments, measurements, deploy sensors and things like that. But even then, the initial condition is not exactly known. So what people usually do is they do so-called data simulation step, where they collect observational data, which in my case, I'm going to assume that the observational data corresponds to the measurements of a solution at a particular time t. These are the positions where I put sensors in the domain and I'm measuring the actual solution. Of course, any measurement or observation has some error, which I'm going to assume that the errors are IID and they're Gaussian with mean 0 and some standard deviation or variance sigma squared. The sensor locations, I'm going to assume I have R sensor locations. In the example I'll show you, I think R is equal to 10. And for the theorem, I'm going to define this quantity I call delta, which has a confusing looking definition, but basically delta tells you for every point in your domain, what is the furthest sensor from that point. In other words, if you draw a circle with or a sphere with radius delta, there is guaranteed to be a sensor in that sphere, right? So have that definition in mind. Then with that, we have the following methodology that says, for every time for which you have data, do your SMS evolution to get the parameters at time theta, but then make a correction and make that correction in a way that the difference between the approximate solution, the numerical SMS solution, at the sensor locations and the observations are minimized. I won't go into details of how we do this minimization. It's a straightforward Newton, essentially Newton type iterations to minimize this. But the theorem is kind of cute, so I'll state that. That says for any epsilon, this is the threshold of your accuracy that you want to obtain, as long as the spacing between the sensors satisfies this upper bound, where LU is the Lipschitz continuity of the true solution of the PDE, and LU hat is the Lipschitz continuity of the approximate solution. So I'm making additional assumption in terms of the solutions having Lipschitz continuity. In that case, then the expected value of the difference between the true solution and the approximate SMS solution is always bounded by this constant, where this part of it is because of the noise in the measurement of data. If you have no noise, this would be 0, but we always have some noise. And this has to do with sparsity of your sensors. If you had sensors everywhere, this would be basically 0. But because we don't have sensors everywhere, there would be some approximation errors that will be made. And the sum of these two incorporate those types of approximations. But nonetheless, if this, this expression is satisfied, you can control how much error in your data simulated solutions you will have. Here is the example again with Krumatov-Sivashinsky. The top row is the ground truth. Look at the bottom row. This is the solution with no data simulation. This is the solution itself, and this is the error. And you see that because this is a chaotic system, even slightest errors in the initial conditions grow over time, and your errors get pretty large after about 20 time units. Now, these two are the SMS solutions with data simulation. This row is data simulation where I didn't add any noise to my observations. I assume I have perfect observations. And you see that the error is you can't even see the colors because the error is so small. It's practically 0. Now, if you have noisy observations, for a long time, you have no error. But at some point, the errors start to grow. And because, again, if you have noise, you cannot really make 100% accurate predictions. By the way, the first 30 time units is where I'm doing data simulation. I'm assuming that I have observations up to time 30. Think of time 30 as the current time. In the past, I've made observations till now, and then I'm going to use this to make predictions. So from this dashed line onwards, I have no observations. I'm just evolving SMS according to the SMS equations, right? But for the point being that for a long time after observations are not available anymore, the errors stay small. All right, with that, I think I've gone a little bit over time. So I'll just put the summary page up here, and I would be happy to take your questions. Thank you.
Can you go 2 slides back?
Yes.
On the Lipschitz coefficient.
Right.
Yeah, this outflow, is that the Lipschitz for the right side of the equation or
For the solution itself.
But
Yeah.
if we have a turbulent system, then this thing would grow
This would not work because those are not Lipschitz continuous anymore. Yeah. So this theorem, we could only prove it under very high regularity assumptions on the solution.
Yeah, I wonder if in the chaos equation there are some turbulence showing up. Does that limit your choice of the delta?
Turbulence, this is chaotic dynamics, but the solution itself at any time is smooth. Okay. Right? There's no non-smoothness in space. Now in time, this is maybe I should be clear. This is Lipschitz continuity in space, in X, not T. But in time, it's chaotic evolution. Yeah. Does that answer?
Yeah.
Yes.
How do you transfer the inner product solutions from Maple or Mathematica into whatever else you're using to solve the matrices and stuff like that?
Yeah, you hire grad students who will type. I guess that's the question. But I also think there are functions that if you're asking for instance, if you're using MATLAB, right, to solve the ODEs, if you're asking about how we get those expressions into MATLAB, is that the question you're getting?
Yeah, well, whoever you do the inner product in Maple or Mathematica, and then there's an out. It's like an in and an out, and that expression symbolically, you either have to solve it somehow, or you put those equations into the.
matrix. Yeah, that's what we do.
Wow.
We just put the symbolic expressions into the
Okay.
matrix.
Is this through the sweatshop of the graduate students, or is there some thing that just says?
Oh yeah,
Put it
there is something that as far as I know, it gives you MATLAB code for a symbolic expression, or Python code, I think these days even, and you just copy paste it into your Python or MATLAB code.
Even Fortran.
Even Fortran, yeah. Well,
Oh,
I use that for Fortran.
just one thing that when I was working many years ago on Einstein's equations, when you write out the whole thing, it's like thousands of lines of Fortran code. So mathematically, you not convert this to Fortran and you print the whole thing. But I realized that a year later because I coded the whole thing with my hands. It wasn't fun. So you can do that.
Yeah, Fortran rules. The co-location points, what are they?
These are basically the up to you for the PDE where you want to pick them. Let me maybe go back to this example, maybe where we use collocation points. So these are, I used, let's see, 128 collocation points. So they're equi-space points in space. So from -10 to 10.
Oh, okay.
Equi-space.
So you just. Yes. Okay.
Choose a bunch of points in your spatial domain. You choose those, and I chose them equi-space. Now, you could do smarter things that we didn't bother to do, like if you know that in certain regions of the domain you have the finer scale structures, you can put more points there and less elsewhere, but we just did equi-space. Does it answer your question?
Total, absolute. Truly, verily.
More questions?
Yeah, just a little question. So in this, actually, okay, you're right on. I was wondering if there's any, you mentioned something about the activation function. Why did you use tangent hyperbolic again? Over other ones?
Yes, no particular reason. We just used that one. We also tried the softmax one. It works just fine, like this one. What we cannot do is to do it ReLU yet, because I need some regularity of one of my assumptions was that the basis functions, in this case activation functions, are at least 4 times in this case differentiable in space. And ReLU is not. We're working on a weak formulation of this methodology where you could potentially eventually use ReLU. Yeah.
Any more questions? Well, let's thank Mohammed again. Thank you.